Welcome to Mind of a Scientist. I'm excited to introduce test engineer at Lawrence Livermore Labs and electric motor aficionado, Jacob Aman. Thank you so much for joining us today.
Hi, Milo, and hi, everyone. My name is Jacob. As Milo said, I'm a test engineer at Lawrence Livermore National Lab. The National Lab's over in Livermore in the East Bay. I've been a test engineer now for 2 years. I really enjoy my job. I get a lot of hands-on activity in the lab. As a test engineer, I validate requirements and make sure our designs meet the requirements, and have to create tests that validate these requirements. So my job involves setting up experiments, doing data analysis once you run your experiment, and writing lots of software to automate the experiments and to make my life easier. And so I like my job because I learn something new every day. And leading up to an engineer, Milo asked me this question a few days ago about what made me choose engineering. And I had to do a little bit of thinking, and I think what made me start thinking about engineering was when I was in 4th grade. I took a Lego robotics class, or as a Lego robotics program that was offered at our school. And our challenge was to build a Lego robot that was going to compete against other students' robots at other schools. And this robot was going to mimic the Mars rover. And so our playing field was a 5-foot by 10-foot playing field, and it had obstacles that represented obstacles that you'd find on Mars. And our robot had to be autonomous and had to go navigate these obstacles and do the little challenges on the course, and then come back to our base. And so we wouldn't be able to touch the robot once it left our little space on the board, and it had to navigate this large playing field. And so that got me interested in engineering, and I got my bachelor's in mechanical engineering. And while I was getting my bachelor's in mechanical engineering, I had the ability to take a course on electric machinery. And while I was doing this course, we would learn the theory of how these electric machines work in lab. And then we'd go to lab, and I would work hands-on with the professor, and we would figure out, how it actually worked. And then we would compare, the theory to the experimental values. And so you could really understand how it worked and what was going on. And so after I graduated, I worked for like a year, and I was so interested in electric machinery that I was like, hey, this is something that I would ideally like to have a career in. And so I got my master's degree studying electric motors, motor control, electric machinery, and power systems. And getting a master's degree is different than a bachelor's in that you really are focusing on something specific. And a lot of the times you almost have to teach yourself with some guidance from professors. And so I guess one lesson that I could probably give you guys, or one takeaway, is that getting started and learning something new is very challenging. And I found it challenging because there's so much information available to you. There's the internet, there's the library, there's articles, journals, academic publications. And for me, finding a book that taught me electric machinery was very difficult because there's so many options. And so essentially I would go to the library, and they would have 20 different books on electric machinery. And I looked through each book, and some of the books were very detailed and hard to understand. And then others were not detailed enough, too simplistic. And then there's other sources that just aren't that great. And so you really have to look and find something that's going to be the right fit for what you want to learn, and it's going to take time. You're not going to find it right away. Today, I'm going to teach you about electric motors, and electric motors are really exciting because right now they're found everywhere, and now with everyone's vehicle becoming electric, it's really exciting. There's lots of new technology coming out. And so today I want to give you an understanding of how these motors work and how the conversion from electrical energy turns into mechanical rotational energy. And so first of all, why should you care about how electric motors work? Well, according to the Department of Energy, which is a US agency, 68% of all the energy produced is used by electric motors. In your house, you could probably think of a few examples. So you have like fans in your house for cooling, you have your electric toothbrush, you have your washing machine. All these have electric motors and you use them almost daily. They have, and then in industry, you have motors that pump water. Here you can see a picture of, these are motors in a pump house. And so in California, there's many pump houses. This is how we get our water. And this motor turns a pump that's located down in the ground and pulls up water. And this is how you get water to your spigot in your house. And so if we didn't have these motors, then it'd be very difficult to get anything accomplished. The other reason you should care is by 2035, all new cars and passenger trucks sold in California will be zero emission vehicles. And so that basically means it's going to have electric motor. And so by listening to my presentation, well, hopefully you'll understand how it works, and maybe you'll see some benefits or some drawbacks to having an electric motor. There's three types of electric motors. The first type of electric motor is the permanent magnet motor. And that's this motor that I show on the left here, and it's been painted green. This motor has permanent magnets in it. These permanent magnets, I'll get into this a little bit later, but they're right here. And then the second type of motor is the induction motor. This is what Nikola Tesla conceived. And in this motor, there's no permanent magnets at all. Essentially, you have the rotor, which is the part that spins, and it's been pulled out of the motor right now, is made of just aluminum, basically like a cast aluminum, and the cast aluminum is cast into the steel, which has slots in it. And then you have reluctance motors. The reluctance motor, you can see the rotor is made of steel, and then it basically has these air pockets that are these really detailed air pockets that are in the actual rotor. And so the most common motor would be the permanent magnet motor and the induction motor. The reluctance motors are a lot less common. So what is an electric motor? An electric motor converts electrical power to mechanical power. And I denote electrical power, this PE, and the mechanical power is PM. And so you can think of a drill. Here you have your standard hand drill, and it has batteries which store the electrical energy. And when you press the trigger, the electrical energy is converted to a mechanical power, and that causes the chuck and the drill bit to spin. It's also important to note that all motors can also act as generators. And so instead of converting electrical power to mechanical power, a generator converts mechanical power back into electrical power. And that's how you get your power in your home. And there's an example of this is your hybrid vehicle. Imagine like the Toyota Prius. The Toyota Prius, imagine you're getting on the freeway you press on the accelerator, the motor starts to accelerate the vehicle, and you start draining your battery because you're converting that electrical power into mechanical power. Well, now, you're on the freeway, you want to get off the freeway, so you have to hit the brake. When you hit the brake on a hybrid vehicle, the motor, the electric motor, will turn into a generator, and it'll basically suck power out of your motion and put that back into the battery. And so the reason they do this is because you get good all-around efficiency. You just restored that energy that you put into motion back into your battery. And so so that's something I just wanted to point out. So now I'm going to go into power conversion and how the electrical power is converted to mechanical power. And so power is torque times speed. And so what is torque? Torque is called a force at a distance. If you look at this picture of the dragster wheel that I have, you have your dragster wheel, and it has an axle, and it also has a place where the tire contacts the ground. And so the distance between the axle and the ground would be your distance, and then your force is the force that's exerted between the tire and ground. And so if you multiply the radius times the force, you get torque. And your speed, so the speed is also called an angular velocity. That's just a fancy term. And so the speed times the torque equals the mechanical power. So now I'm going to discuss the electrical power. Electrical power is a bit more complicated, but hopefully I'll try to make it simple so that you understand. So electrical power is voltage times current. And so to understand what voltage and current are, there's a really good water flow analogy. And so basically, if you look at this picture of this guy drinking this green shake, pressure would be the suction that he exerts with his mouth. And when you suck on a straw, that creates flow through the straw. And so the amount of flow that you get is dependent upon how big that straw is. If you have a small straw, it's really hard to get any flow of shake. It's really hard to drink the shake. But if you have a larger straw, it becomes a lot easier. You get more flow. And so you can think of this pressure as the voltage and the flow as the current. And instead of, in electrical circuits, you have flow of electrons. And so that's what current is. And so this power conversion, basically the mechanical power has to equal the electrical power. The power isn't lost mysteriously, nor is it created mysteriously. There's no such thing as free energy. And so you have to realize this what you put in electrically is what you get out mechanically. And so now I want to discuss the main components of electric motor. And what we're going to do is we're going to go into what the voltage and current is in a little bit more detail, give you a bit more understanding. So there's two main components to the motor. There's the stator, which is the stationary part. And the stator is essentially this green piece, which is called the stator yoke. And the stator consists of coils, which are conductive wires wrapped around. And so the stator is the stationary part of the motor. And it basically, this green part, the stator yoke is what holds the coils in place so that they don't move when the machine's operating, or they don't vibrate out of place. And you also have the rotor, and the rotor is the part that rotates. This would be the part that spins the tires on the car. And in this case, the rotor consists of permanent magnets which are these small rectangular pieces, and it consists of a rotor core. The rotor core essentially holds the magnets in specific positions so that they don't move. And so this is, there's 4 components to the motor, to the permanent magnet motor, and these are the components. So now I want to get into how the magnets work. So when you make a permanent magnet, the magnet does not start off as magnetized. Essentially, when they make the magnet, they take a bunch of really finely ground up particles, and they put it into a mold, and they compress the mold, and that creates your magnet shape. And to turn this magnet shape into a magnetized magnet, you have to exert a really large magnetic field on the magnet. And so you exert this really large external magnetic field, and then you remove the field, and the permanent magnet will hold the magnetization. And so this magnetization, which I show to the right, it's essentially, it's oriented so that you have a north and south pole, and the magnetization is the result of electron spins in the atom aligning together. And so these magnets create these external fields that radiate from the actual physical material. And these fields are called the magnetic flux density. And so here you can see I've drawn the fields. They start at the north pole of the magnet, and they circle around and go to the south pole of the magnet. And these fields are given the units of Webers per square meter. And Weber is a unit of magnetic flux, and then meter squared is a unit of area. And so these fields are like essentially a density. And so if you think about it, the fields really close to a magnet are going to be really strong because they're very dense. And then the fields further away from the magnet are going to be a lot weaker. And so if you think about it, if you take a magnet and you move it towards your fridge, all of a sudden it gets really, really strong, and at some point you can't even stop it from sticking on the fridge. Well, that's because those fields get really dense as the magnet's close to the fridge. And so if you move the magnet, if you rotate it, the fields orient themselves the same way with respect to the north and south pole. And so this unit of Webers per square meter is also called the Tesla, after Nikola Tesla. So now I'm going to dig into like how the motor works a little bit more. I'm going to give you, I've kind of drawn out this simplified motor. So this motor, essentially you have a magnet, and you have 2 coils. You have coil A, which is this lighter yellow, and coil B, which is almost this orange color. And these are the most basic components that you can use to create an electric or permanent magnet motor. And with this motor, you essentially would apply a current to coil A and a current to coil B. And when this magnet spins, you induce voltages in the coil. And we'll go into what those voltages are in the next slide. So the first concept of understanding the electrical parameters of the motor, Faraday's law says that any change in the magnetic environment or magnetic flux of a coil or wire will cause a voltage to be induced in the coil. And this is Faraday's law right here. Faraday's law says there's a voltage induced if there's a change in flux with respect to the position of the magnet. And this is also multiplied by the speed of the motor. And so I'm going to get into a little bit more detail about what this change in magnetic flux is divided by the change in position. So don't worry if you don't understand it right now. We'll come back to this. So here's how kind of like a motor works. Basically, I have 3 different diagrams of the motor, and each diagram of the motor, the magnet's in a different position. We start off with the magnet oriented in 0 degrees, where the magnet faces coil A. And then the second one, we rotate the magnet. So the magnet's now positioned between coil A and coil B. And then the third image, the magnet's oriented at coil B. And so you can see if you like take this coil and you almost like look at it directly, when the magnet's oriented towards coil A, you can see that there's some fields going through it, and these fields are going perpendicular through the coil. If you look at coil B though, the fields are going parallel to it. And so you can get the idea that for coil A, you have all these fields going through it, and coil B, you have none. They're just going parallel to the coil. And then when we rotate the magnet now you have a few more fields that are going perpendicular to coil B. So your fields you're starting to get some of the fields through it. And if you look at coil A, you essentially lost some of the fields. So the field density has changed. And now in the 90-degree case, the magnet's oriented at coil B, and you see you have all these fields going through it and none going through A. So you can get the idea that if you rotate the magnet, the magnetic flux or the magnetic field density in the coil is changing with position. There we go. And so there's another law involved in motors, and that's Gauss's law. And Gauss's law says that the amount of flux going through the motor is the magnetic flux density, which I said was Webers per meter squared, times the coil area. And so if you take the area of the coil and multiply it by all the fields that you see going through it, that's the total amount of flux going through it. And so here I have a video that I'm going to share with you guys that will kind of demonstrate, and so you can see the fields changing in the motor. Let me share it. So here on this motor, the magnets are actually located on the outside of the motor, and so you have these magnets, and you can see the fields that are darker color are more dense. So if it like this pink here and the orange are more dense versus the fields that are blue are less dense. And so you can see the fields in the motor are changing with the position of the magnet. And so that induces a voltage in the coil. So now returning to Faraday's law. So again, Faraday's law said any change in the magnetic environment or magnetic flux of a coil of wire will cause a voltage to be induced in the coil. And so this change in magnetic flux divided by the change in position of the motor is what's called the torque constant. And the torque constant is how strong the motor is. And so if you think about like, if you have a bigger motor and a smaller motor, the bigger motor is going to have bigger coils, it's going to have more area, and so you're going to have a bigger area that the magnetic flux can pass through. And so the torque constant will be higher for a bigger motor because you get more change in flux as the rotor rotates. And so kind of putting it all together, we started off with the mechanical power equaling the electrical power. And then we broke it down, said that the mechanical power equals the torque times the speed. And then on the electrical power, we said, the voltage times the current in each coil was the electrical power. And if you apply sinusoidal excitations, so periodic excitations, then essentially what you get is you get that the mechanical power equals the torque constant times the current that you apply to the motor times the speed of the motor. And these, just to note, these current excitations are applied by a power inverter, or sorry, a power converter, or a drive unit. And usually this is what they call power electronics. And so this is like, I believe, one of the Tesla's power electronic packages. And so kind of revisiting the torque constant. So again, like I said, the torque constant's a measure of how strong the motor is. And so what makes one motor stronger than another? Well, it turns out the torque is proportional to the motor's radius squared times the length. And so what's this mean? It means that to get more torque out of a motor, you get a lot more torque if you make the radius bigger. And so ideally, your motor is going to look more like a pancake than a hot dog. So here, this top example, you can see the radius is really large and the length is really skinny. And so this motor has a lot of torque. And then you have this other motor where the radius is really small, but the length is really long. And so motors will tend to look like this upper one, like the pancake, because that's what gives it the most torque. The other thing that gives you more torque is your magnet strength. You've probably heard of rare earth magnets. Rare earth magnets give you the most energy, and that's what they call the energy product. So the higher the energy product, the more torque dense the motor. So what electric motors do cars have? There's pretty much two different types that they've been using in electric vehicles. There's the induction motor, which has been used in the Tesla Model S, I believe the Tesla Model X, and the Audi e-tron. And then there's other motor called the permanent magnet synchronous reluctance motor, which has been used in the Tesla Model 3, the Toyota Prius, the Nissan Leaf, Chevy Volt, you name it, it probably has it. And so what is this synchronous reluctance motor? Well, remember I was talking about the reluctance motor having a rotor that contained steel with air pockets? Well, what they do is they fill the air pockets with magnets. And so if you look on the picture on the right, you see these magnets, and they've been embedded into the steel on the motor. And it looks a little bit different than the reluctance motor, but just think, in the reluctance motor, they would have just removed the magnets, but now they put them in there. And so this is pretty much what most vehicles use. So what's the rationale for the induction motor? Why do they choose one versus the other? Well, there's actually a pretty good reason. So the induction is because there's no reliance on rare earth materials, so no reliance on magnets. And these magnets and rare earth materials are subject to price manipulation. So here's a plot on the right. Basically, China is the main producer of all rare earth metals, and so they control the price. And so back in 2011, there was a huge price spike where China caused the prices of the rare earth materials to skyrocket. And so by choosing an induction motor, then you don't have to deal with the price manipulation. But what's the rationale for the permanent magnet synchronous reluctance motor? Well, you get a little bit better efficiency. and the control strategy is a lot easier. So it's easier to control the motor and have it make it do what you want. And so I believe this concludes my slide. So thanks everyone. Thanks for listening.
That was such an elegant explanation of a really complicated topic. Thank you so much, Jacob. And now we've got time for questions. Stefan asks, is there any situation where a motor would require less torque?
I mean, there are like what they call high-speed motors. So motors where you need a very, very high speed. So think of like a dentist drill. You don't need that much torque, but you need a lot of speed to grind away the material. So that might be one case or one example of a high-speed motor. I think they also use them in like gas turbines to get the gas turbine started, or natural gas pumps.
So Mateo asks, how is the force, the push-pull of a magnet measured, and how is it controlled?
So in the case of a motor, that's a really good question. So in motors, we're talking about torque. So force at a distance. So obviously you would have to measure torque, and in motor applications, like if you're validating or looking at a motor in lab, you would have a torque sensor, and that torque sensor essentially has strain gauges, which are gauges. They're basically really small, like gauges that they glue onto the axle, and they look at how the axle's like deforming, like how the material's deforming. And so that's one way that you could measure the torque. How do you control it? That's a question that's actually also pretty common. So a lot of motors, when they actually control them, they look at the current that they're applying to the motor, and that current multiplied by your torque constant equals your torque. So if you have a good knowledge of what your current is, then if you have a good knowledge of what your torque constant is, then you can get torque. And so in vehicles, when you're pressing the gas pedal, you're applying torque. And so in electric vehicles, they have control loops that are running at really high speeds that are looking at how much are you pressing the pedal, how much current am I applying to the motor, am I actually applying the correct amount of torque that the user is asking for.
Now, I know you mentioned the Lego Robotics Club, but Aaliyah is wondering, were you always interested in mechanical engineering?
Yeah, I believe so. So when I got in to my undergrad, I started off as electrical. So, and then I switched over to mechanical. So back when I was in high school, I actually didn't really know the engineering term for what I was interested in until I sat down and started applying to school. So, so I didn't know that mechanical engineering was what I wanted to go into until I sat down and was reading through the course manual. And I would say I was pretty much always interested in mechanical engineering. But my interests have somewhat changed. Now I'm more interested in electrical systems. So,
yeah. Jake asks, are there any promising improvements you know of in the field of electric motors?
Yeah, I mean, I could mention one. So I believe the Department of Energy is studying new magnet technologies such as exchange spring magnets. Essentially, you want to create more energy dense magnets that don't use rare earth materials. That's kind of like the goal. Or you create more energy dense magnets that, and so you can make your magnets smaller and use less material. So that's one pretty promising improvement. Most the improvements in electric motors are related to like the control strategy. So how you control it, how you apply currents to it. That's where most of the technology is right now. And so these motors, you know, when they heat up, their performance changes. And so your control strategies have to adapt to those changes. And so, so the control strategies where most the new technology is coming into play.
Mm-hmm. Are there any of the motors you work on sensitive enough to be affected by different altitudes or by being in different parts of the world?
I don't believe so. So, so that's one of the nice things about motors is like, you know, if you drive your car up to the mountains, you know, you're changing altitude and the car loses power. But the nice thing about electric motors is their performance doesn't really change with respect to air pressure. Different parts of the world, I guess potentially, you know, if you go to some place that's really hot, your motor won't cool as well. And that could be a problem. So the magnets, they can demagnetize if you get them hot enough. And so if you don't cool them enough, then you'll demagnetize them and then your motor won't work that well anymore.
Kaylee asks, what are the risks in your profession?
Let's see.
Do you risk being electrocuted, or is there radiation ever? Or?
Yeah, I mean, there is like a risk of, I don't deal with like systems that are high voltage enough to risk electrocution. There certainly are risks of radiation, but those are mitigated because of safety, you know, safety procedures that you follow.
Mm-hmm. Mm-hmm. Sophia asks, how can you test how efficient a motor is? Do you use encoders? How are encoders similar to motors?
Okay, yeah. So I guess I'll address the encoders first. So an encoder is a optical device that you put onto a motor, and the encoder measures the position of the motor. And so basically the encoder has like these, it's basically like an optical wheel. It's a wheel with a bunch of holes in it, and there's a light source and there's a detector on the other side. And so as the optical wheel spins, you see a bunch of flashes on the detector. And so that tells you pretty accurately what the position of the motor is. And so most motors are paired to either allow you to see what the position of the motor is, or they take the derivative of the position to get the speed of the motor. And then the way that you would determine how efficient a motor is basically you would have to have a torque sensor and a speed sensor. So you know what your mechanical, you have to know your torque and your speed of your motor. And then you have to be measuring the voltage that you're applying to the motor and the current that's flowing through it. And so if you know your mechanical power and your electrical power, then you could see what's lost. And so you'll have losses because of resistance. There'll be frictional losses in motors because the magnets are moving. There's also eddy current losses. So these magnets induce eddy currents that will act as friction. Um, so yeah, so basically comparing, the power you put into it and the power you get out, that's how you look at the efficiency.
Mm-hmm. Stefan asks, can price manipulation or scarce magnetic metals lead to less efficient motors? And do you think this will be an issue in the future?
That's a really good question. I mean, by less efficient, if a manufacturer had to go to a using a less energy dense magnet, then your motor is going to have to be a lot larger to get the torque that you need. As I said, the energy product is proportional to the torque, and so if you use a lower energy dense magnet, then your motor is just going to have to be like a lot bigger. And so I believe they're trying to make improvements to lower energy density magnets like alkyno magnets to improve their performance, because I believe alkyno is not rare earth. So if you can improve like the lower end performance of non-rare earth magnets to be somewhat comparable to rare earth, then that might be a way to get around the price manipulation issue. But yeah, certainly this can be an issue in the future, because the amount of car manufacturers that are making magnets is going up, and we're consuming rare earth materials quite rapidly. And I know that the US has started to ramp up rare earth production here so that we can try to meet the demand.
Jacob, I just want to say thank you so much. That was such a brilliant and such a concise explanation.